So thank you very much for having me here at the research method training from Humboldt University in Berlin, or /Dagstuhl today. Today over here, I'm happy to have you with us today. And and today I'm going to comment on impact in software engineering research. A couple of facts about myself. I did my PhD in 1997. I'm a professor at Saarland University in Saarbrücken, and since 2019, I'm also faculty at the CISPA Helmholtz Center for Information Security. I'm an ACM Fellow. I got an ERC Advanced Grant. I have a SIGSOFT Outstanding Research Award. And last week, which apparently is my impression, which at least according to social media might have been my most impressive feat so far, I have accumulated over the years 6 10-year impact awards. These are test of time awards that papers get 10 years after their original publication, and it appears that this is a very, very rare thing. And since these are impact awards, yes, I think I can comment a bit about impact. So let's start with what is impact anyway? And this is a general question about, well, what is the impact of your life, in particular of your professional life? How do your actions change the world? We as researchers, we want to make the world a better place. And this is something that gives meaning and purpose to our professional life, also to our private life, of course, but here I'm talking about the professional life. So we want to change the world, want to make it better, and this is why we do research in the end. This is a noble goal, and yes, I'm very happy about that. What is it that makes impactful research, or what is it that makes good research? The elder statesman of our faculty, that's Professor Holtz, gave me 3 metrics by which he would go and detect whether some piece of research would be impactful. He said that, is this hard, or is this something that anyone could have done? And they call this intellectual challenge. Second question is your research specific to a context, or can it be reused again and again? And this is what he called elegance. And lastly, which was a rather recent addition, can someone make money with it? This is usefulness. And according to these 3 metrics, we can also come up with an innovation metric, which is the delta in any of these metrics. So do we have an increase in usefulness, an increase in elegance, and likewise? Now, by these 3 metrics, software engineering actually has a difficult time depending on the perspective you look at it. So I've been working with a number of communities outside of software engineering, and I also have faced a couple of concerns over time. So if you look at software engineering research from the outside, suppose you are a programming language researcher, then you find that software engineering totally lacks intellectual challenge. Where are your type equations? Where are your equations anyway? I mean, where is your big formal building that you create? Not enough of that in software engineering. Same thing from a formal methods perspective. Software engineering is so inelegant. It's full of details you cannot control, starting with humans in the first place. So where is the nice, elegant abstraction in software engineering? From an industry perspective, it's actually the other way around. There we lack immediate usefulness. Why can't I just download your super duper method and apply it right away and get immediate returns? But no, you can't. Oh, your tool doesn't work on Fortran 77. Oh, that's too bad. Well, we thought it was useful. Well, it isn't. And since I'm now working in a security research center, I can tell you that from their perspective, I am a full theory person, because what I'm doing is always a bit too abstract for their taste, and they want something that gets them another security vulnerability immediately, rather than a general principle that in principle could contribute to, when they hear the word principle, that's already theory for them. So we're having a bad time with all these different perspectives, and it's actually difficult to navigate, to not stumble into any of these obstacles. And yet, in some way, I have made my way across all these concerns towards impact. And I'd like to share a few of my personal path to this impact. And this is actually fun because in advance, I had no idea where I would be going. And even today, I have no idea where I will be going in a couple of years. Maybe that's a good thing for a researcher. But at least in hindsight, I try to understand whether there are any constants, any invariants that help me get in this path. And this is what I want to share today. So I did my PhD in Darmstadt. Sorry, not in Darmstadt. Well, I started in Darmstadt with Gregor Snelting, who was my PhD advisor, and then moved on to Braunschweig, where I did my PhD. And his idea was to formally describe variants and revisions of software engineering using feature logic. I'm not going to comment too much on what feature logic is, but the idea was to come up with a unified model for configuration management. And yes, this worked. I got a couple of papers out of it and a couple of, and a PhD thesis and whatnot. But in the end, when I'm looking back now and trying to find out whether I learned anything from that, there wasn't much. So actually, in hindsight, I think that in this kind of research, I did plenty of things wrong. That's because, well, I missed the problem. Nobody would ever want to apply my techniques. Actually, I didn't even care to prove my techniques or to evaluate them. Yet I got plenty of papers accepted, which today would probably be a bit more difficult. I was modeling for the sake of modeling, which was, well, it was a model. So there we went. It was a nice model. But in the end, my model didn't make any difference. And the good news, however, was that that all this looking into individual versions and dealing with them enabled much of my later work. So that's the good news. After my PhD, I had the option to go work in the IT industry, but at the time I found the standards and topics rather disappointing. The standards in particular, who wants to do that kind of development? And anyway, as a programmer or developer, you're always second rate, in contrast to whatever car engineers and whatnot. And academia seemed like a fun alternative, and I was very much socialized at the time by open source development and their standards and the way that they develop software. And this was also what influenced my first, well, bigger work. During my PhD, I programmed a lot, and debugging was something that I found very hard. So with my student, Dorothea Lütgehaus, I built a nice debugger front-end, graphical front-end for command line debuggers like GDB. This then became, was actually adopted as a GNU project, which gave me quite some street credibility with developers, at least if you are 40 years or older, because, well, today you're using different tools. But this was also downloaded like crazy. I got postcards and everything. And this really comforted me from my more theoretical PhD work at the time, because, well, I was actually able to create something that was useful. It wasn't much from an academic perspective, but at least it showed me that, yes, you can have impact through usefulness. And there were a couple of lessons I learned from that. And the first lesson was that I would be working on a real problem. And the real problem here was debugging. Apparently, there was not enough support for helping people with debugging. The second thing I learned was to assume as little as possible, namely to not interfere too much with existing processes, but rather make things fit there. And the third thing was that I needed to keep things simple to use, simple to deploy, and this would eventually create impact. And these are lessons which I would cherish and repeat again and again. After my PhD, I was looking up for a new topic because, well, after your PhD, you're supposed to change topics. I was in a postdoc position there, and I thought about, well, I had this debugger and I had worked on version control. Is there a way for me to put these two things together? And this is where I invented the technique now today known as delta debugging, which would bring together debugging and version control, which actually neatly determines changes that cause failure or small parts of the input that cause failure these are really, this is a pretty simple algorithm, actually. It is very easy to teach. It's easy to understand. It was 25 lines of Python. That's the entire implementation. It sounds small, but I actually spent 2 years on developing these, which is incredible. from in hindsight, how on earth did I spend so much time on this little thing? But it really took some time to get it as small as it was, as it is. And this was extremely well received. Actually, talking about delta debugging was the one thing that got me my my tenured professor position at Saarland University, because, well, people liked it, and yep, and it came with formulas and came with proofs and everything. So yep, this was a nice package altogether. And here again, I was working on a real problem, which was very much recognized. I assumed as little as possible. Well, version control and automated testing wasn't always there at the time, but now 20 years later, it's actually around. I wanted to, I deliberately kept things as simple as possible, and I had a sound model because in some way delta debugging was my version model reborn. So this was a bomb, and this got me quite some attention, and I published a couple of papers on various applications of delta debugging. And at some point, a colleague of mine asked my advisor, so are you going to continue delta debugging forever? No, I'm not going to do that. I want to do something different again. And this is how I got to the field of, how I co-shaped the fields of mining software archives, where again, my expertise in looking at version control helped us analyzing the data that would be in these version archives. And it turned out that we were among the very first to actually systematically analyze these things. This was with my student, Tom Zimmerman, who was my master's student at the time, who currently is one of the most cited researchers, even more cited, I guess much more cited than I am even. He's president of SIGSOFT and whatnot. So this was an absolute bomb. And this is actually the effort of a team. So there was Stefan Diehl, there was Peter Weisgerber, there was Tom Zimmerman and myself, and we all brought this together, figuring out, for instance, where in a piece of software one would find the most vulnerabilities, bugs, and whatsoever. We had a handful of competing groups at the time, so we were actually lucky because there were others working in similar directions, and we were just weeks ahead of them, which is great. But today, this whole field of mining software repositories has become tremendously huge. The paper which we did in 2004 has more than 1,500 citations at this point. It's probably one of the most impactful papers in the last 2 decades or so. And this is now being used all over the place. It's being such telemetry on developers, if you wish. It's being used at Microsoft, at Google, at SAP. So this is quite a hit. But for this at the time, we had to learn everything. We had to learn what information retrieval meant. We had to learn what precision and recall was. We had to explain these things in every talk because people didn't know these terms, because such a large scale empirical work was not yet this much established. So we had to learn plenty of new things here at this point. And this is also something, all these things were entirely different from what I had learned before. So this is another lesson to be learned. It helps to go totally out of your comfort zone, even if you do have to learn new things from the very beginning. And this is what we did here. Today, so I kept on doing some mining software repository work, but today we are far after the gold rush. So there's quite a number of papers where people find out, oh, we downloaded this data set and we found a correlation between A and B. How is that? Yeah, it can be exciting. Frequently, it's not as exciting as it was at the time. And this is also when I learned to get out of a field when it is too crowded. However, this opened up opportunities for other work. For instance, yeah, this was a nice thing. What we had were these distributions of were these distributions of bugs in software system. This is actually Firefox, and each rectangle in here is a module, and the redder a module is, the more security vulnerabilities it had over time. So we wanted to figure out, for instance, are these bug densities related to test quality? Well, that's an interesting question, actually still open question. So we wondered, how can we measure test quality? And so we said, okay, we're going to apply mutation testing, because from textbooks and from own teaching, we knew that this was the best way to find out how good a test is. Mind you, mutation testing is the art of throwing in artificial bugs into a software system and then figuring out whether the tests would actually be able to detect these artificial bugs. And then we found out that, to our big dismay, there was the small problem of equivalent mutants, which was sometimes slightly mentioned in the papers on mutation testing. Oh yeah, you can have this problem. This is actually a problem, and we don't know how to solve this, which turned out to be a very big problem for us, because a large majority of our limitations we threw in were equivalent mutants. Equivalent mutants means you may make a change to a piece of software which actually doesn't change its semantics, and therefore a test cannot find them, and therefore you have plenty of false positives when doing mutation testing, because you find out, oh, my test cannot discover this mutant. Well, it turns out it's an equivalent one, and determining whether a change in the code changes the semantics is actually an undecidable problem. So boom, it's big. So being the engineers that we were, we built a solution for this, which became a rather popular tool called Java Launch, in particular with a cool name. And so we made quite a number of contributions to mutation testing at the time. And then in 2011, something weird happened. We found out that we could actually do entirely without mutations, and we simply by looking at whether an assertion in a test would actually be influenced by earlier statements, and the more statements that would influence an assertion, the higher its capability to detect errors, which turned out to be a good alternative to mutation testing. And this is actually a paper which just last week got us the 6th Tenure Impact Award. The fun thing was that, so my PhD student who did all that, that's David Schuler, first started with mutation testing, and he built a great infrastructure for mutation testing. And then in his last paper, he found out that all of this infrastructure actually was not necessary. And that's weird. But at the time I said, well, you know, with this piece of work, you're actually negating what you did before, right? Yeah, but yeah, I understand, for the sake of research, it has to be, you actually have to go and nix your own beliefs and your own investment if it's for the better. And that's also something which today is still one of the turning points here, because it also means that you have to be ready to drop what you've done before if you come up with a better solution. And here again, this is simply keep on moving to new directions. Where is the pain point? Where is the trouble? And you can find out these pain points frequently simply by applying these techniques. And what is it that you can do? Maybe you have a solution for that. And if you have a good solution, well, sometimes even identifying the pain point already can be a research contribution, because it steers the research towards that pain point. But if you also have an idea of how to solve that, that's a good thing. So there's plenty of more things I've done. Well, I've been around for quite some time. I did automatic repair. Actually, our paper was almost done when Wesley Weimer and Claire Leguez came out with their much better work. So yeah, so we scooped others, they scooped us. Automatic parallelization is a piece of work which I did. I did automatic website testing, which has become a pretty flourishing company these days. We did app mining and app analysis, plenty of stuff. I still do lots of fuzzing and test generation. And recently I have embarked into literate programming. What is literate programming? Literate programming means that rather than simply writing code, you're mixing code and text to form a greater whole. And I'm doing this, and I started doing this for teaching. So I'm working a lot with Jupyter Notebooks these days. So here's a simple example. This is a piece on dynamic slicing, which will go live actually tomorrow. So you can see here that this is fun stuff. So I'm mixing up text information. I'm mixing up code in here, which I'm writing, and then I'm applying my own infrastructure, which I wrote in here, which I actually all wrote in this style of putting together text and code. And Jupyter Notebooks are great because they can produce really, really nice, rich output in here. And I'm now using these for teaching because I'm coding things, because I'm explaining things. But I'm also using these for re-implementing existing techniques and figuring out what their pain points are. And I'm using these for prototyping own research, meaning that when I have a new idea, I'm building a Jupyter Notebook and I'm showing off, hey, folks, here's a small prototype that works in Python, for Python, and these are the results. Isn't this something that we could build for real? For real, meaning larger systems, other programming languages, say C, say Java, not Python, which is from too many still being considered a toy language, although every time you start Netflix, it's all Python. But this has become such a nice style of communicating research results just as well. There's lots and lots of potential in here, and this is what I want to turn, which I may well turn into some future research direction here too. And the side effect of this is this also helps in conserving our research because, well, standard thing is some student builds something and then builds something, lets it run enough such that we can make papers out of it and possibly a PhD thesis. But in the end, what you have after the PhD thesis, you have these huge heaps of smoking heaps of wire and duct tape, which sometimes work, which mostly work, but which are almost impossible to reuse again. And by adopting this literate style, of this notebook style, we're having an infrastructure which is much more reusable and which is much easier to communicate to others. And this is something which I cannot recommend enough these days for prototyping research. And there's lots of things to try. If you're interested in that, actually, I do have 2 textbooks on them which use this style. One is called Fuzzing Book, well, as the name says, on fuzzing. And another one, which is appearing right now, 1 chapter per week, is called debuggingbook.org on automated debugging techniques. So, and with this prototyping, I also learned a lot, namely to build prototypes and to build prototypes first. And I build these prototypes myself, or my students build them, and then we can exchange things. But as long as they're prototypes, they're much easier to handle. And this allows us to learn the pain points of existing techniques, and it allows us to get the algorithms and the approaches right first before embarking on implementing them for Java or C, where we already know that this may take months to years to build an infrastructure. And it's much easier if you know that this is going to be successful. There's areas which I stayed away from, notably software processes, formal methods, modeling architecture. And there's reasons for that. The main reason is that all of these assume large changes in existing processes and existing environments. And this is something which goes against my principle of assuming as little as possible, which does not mean at all that these are not important. Actually, these are very big problems, much bigger than these problems are much bigger than the problems I'm trying to solve. But the thing is, I personally cannot get a handle on them. For me, it's difficult to find out what exactly is the problem, to formulate what the problem is. For me, it's difficult to find out how I possibly could have impact. And it also is difficult for me to find out how to measure this impact. So, I am, in a way, I am working in areas which are better lit, and where I'm trying to find the places where I can add my 2 cents to the body of research. But at least these areas that are well lit, at least from my perspective, still give me some opportunity to, well, to make them even better lit. Although I know there's plenty of areas which deserve a much more light and which may be far more important in the long run. This actually brings me to the topic of how to measure how to measure impact. We said in the beginning, what is your purpose? You want to change the world, and how do you measure that? In advance, it's pretty much impossible to assess how your actions will change the world. It may be possible to assess how your actions may change the world, but this is extremely subjective and also speculative, which is why our employers go for all the usual metrics, publications, money, students, citations. These are all neat. And yes, we can measure these. Anyone can measure these, actually. It's not very difficult to produce the sum of of funding or to count students and whatnot. But all of these are very indirect indicators of what actually matters. And the intersection between these two, what can be measured and what actually matters in research metrics, is not very big. You see, while you're going for tenure, it might still be okay to go for these metrics because your future employers may look at these, or these may be used for filtering. This may be used for filtering out. And indeed, if you have no publications at all, or if all your publications are in some second or third rate places, this may indeed be counted against you. In the long run, though, you want to be remembered for your tool, for your algorithm, for your book, the one thing that really changed things. And you will not be remembered for doing well in a metric. You will not be remembered for being the one researcher with an H index of such and such. That's not the thing. No, if you have the Schulze algorithm, if you have the Hahnemann book, whatsoever, okay, just making up names here. This is the one thing that really counts. And when you're talking to others, when others talk about you. And remember this, so go for metrics until you have tenure, but after that, no, go for the important things, go for the things that actually matter. With all this, I'd like to point out that when I'm talking about my own path to impact here, we're having a severe case of survivorship bias, meaning that I am the one who survived this entire model, and here I am with all my success, and I can of course now go and tell you, yeah, all of this helped, and all of this eventually got me to the path. But you also have to consider that along this path, there's many people who've tried a similar path, who may have done better work even, but with less success. And we know far too little about these who failed in the academic process, because these and their experiences could actually be far more important to figure out, not only what to do from the few who survived, but actually what to avoid from the far more people who did not make it to this point in their academic career. The picture here actually comes from the Wikipedia entry on survivorship bias, and that this is a great example on how to misinterpret the findings of people who survived. So, how can you have impact? And what are the ways that you can have impact? Well, there's many ways. First, of course, as a researcher. Why do we have research in the first place? Because researchers are supposed to take risks that no one else takes. Research is risky by construction. You don't know what you're aiming for, and you should expect to fail and to fail again, because this is built in. Once you have tenured, the principle of tenure is to make it possible for you to go for even grander challenges, to take even larger risk. And please take that gift and make use of it. Work on the grand stuff. And this is something I want to emphasize again and again. You should go and make use of that. You should build things. You should try out things. You should find out what works and what doesn't. Find the pain points. What is it that doesn't work? What is it where you can help? This is one of your most noblest, one of the most noblest expectations, one of the most noblest ways that you can give back to society what society expects from you. This is not always easy, but in particular, since we don't always have the resources to change the world, which means that, well, if we cannot change the world, we can at least work on a model of the world that is work in the small abstract things, prototype things, do all you can to make things as easy and swift as possible for you, and try to, if you can solve things in the small, if you can solve things in the abstract, maybe there's a chance that you will also be able to solve them in the large with all its fuzzy and hairy details. The second impact is as a teacher. Teacher, of course, is a great way to multiply your message. You should not only focus on teaching the standards, here's how to do version control with Git for the umpteenth time, because there's always a new generation of students which has to learn, but also be sure to teach your research, because that helps propagating it and making it accessible. In particular, in these days of online learning, there's never been a better time to propagate your teaching and to propagate your research along the way. Turn your research into pieces of code, into pieces of work that you can use in teaching, and try to identify those students who are able to work with you and engage them on the topics that you like a lot. We're in Germany, so impact with industry is also helpful and also expected. You should go and definitely work with industry to find out what the problems are and frame your work for figuring out where, so am I actually making the right assumptions right now, or possibly speculative, where is industry going in 10 years, and how could my research be helpful to them at this point? I would advise against working with industry to solve their concrete problems. This is an art form in itself. Work with industry to find the problems, but then come up with an appropriate abstraction that could work in all places, and then again instantiate that abstraction towards your concrete industry partners to find out whether they work. This is a very difficult set of skills. I don't know too many folks who can master all of these and be successful working with industry and working with academia at the same time. Have a look at the works of Lionel Briand, who in my view is an absolute master on that, and who of course preaches to everyone that you should work more with industry because it has worked so well for him. But that is actually difficult. Do not turn yourself into some consulting tool, some cheap consulting tool. That's not what society expects from you. Maybe that's what industry wants from you because you're cheap, but that's not your role as a researcher. Also keep in mind that there's many funding schemes where research is just there to subsidize industry, or where the main point is to subsidize industry. It's not bad to engage in these schemes, but keep in mind that the expectation from industry is not always research, but the expectation is simply money. You can have impact through tools. So if you give out your technique out as a tool, that's a great way to have impact, because people will then know, oh, you're such and such, and you have built a such and such tool. Well, this is so great. Having things out as a tool also allows you to find out what actual users need. It also helps you finding out whether they actually exist. A tool can have far more impact than a paper. Best, of course, is a paper and a tool, but a tool alone already can have plenty of impact. And the good news is that funding agencies, say like DFG, as well as hiring committees, begin to realize this, that impact through a tool can be far more significant than a paper. And yes, impact through tools, impact through research software, impact through software should definitely help you in your career. You can also have impact as a founder. We have Dirk Riele with us today, so I'm sure you will have a couple of comments on that too. But yes, creating a company out of your research can be great fun, pushes your research and ideas into practice. Again, this very much tells you what the market wants and needs and what not. Can be hard to learn, but again, that's a lesson to be learned. The good news is that there's in Germany, you have plenty of support in terms of monetary, in terms of consulting available if you want to take that steps. And this actually means that you can do so without too much personal risk. So, and this is where, again, you learn so much from how things work. This is just amazing. You can have impact as a mentor, which can be the by far most satisfying part of your job, working with people, working with master students, PhD students, postdocs. Wonderful, so wonderful. Talking to smart people who also want to change the world, working with them. This is so ultimately satisfying. Sometimes I really wonder why I actually get money for my job, because there's so many things. There's so many things which are so satisfying. This is just amazing. From my perspective, the one thing to mostly look for in your coworkers is universal problem-solving skills, meaning that people who are able to identify problems and who are able to solve these problems without you having to take them by the hand for every single micro problem they may encounter. These are skills that help a lot in software engineering research because, well, in software engineering research, you're going to encounter plenty of small problems and you will need people who will be able to solve them. And these skills need to be found besides the usual good grades. If you're lucky, you can form your entire group into a team where people help each other and where also the research of individuals complements each other such that they can work together without having you at the center of things at all times. So then you become part of some vibrant ecosystem that you created yourself, and you look around, oh, there's something new coming out here, there's something new coming out there. How cool is that? And this is also very, very satisfying. This gets me to the point of the environment where you're working at. So when I was hired at Saarbrücken University, now some 20 years ago, I was hired into a tenured position, although I was among all candidates, the candidates with the fewest publications. That's something I still have to I still don't fully comprehend. The thing was, and the thing still is, well, the hiring committees at the time, and still do, they read the papers of the individual candidates and they liked my papers, my few papers. So they hired me, which was cool. And during my entire career, I never got any pressure or even incentive on papers, on citations, on funding, or anything. The only expectation of my colleagues here was long-term impact. This is what they expected from me, and this is how I aligned my research agenda for that. And yep, I delivered on that. And so if you are lucky enough to be in a place which actually cares for such long-term impact, where everybody contributes to the long-term impact, not only of each one personally, but actually also to the long-term impact of the entire environment. Yep, this is a strategy which, with a bit of luck, can well work. And same is actually also true for my employer right now, for CISPA, who will be hiring some 100 new faculty in the next, how many years? In the next 7 to 8 years, who is aiming for a total of something between 800 to 1,200 PhD students, or 800 to 1,200 researchers overall. These are amazing figures, and it almost sounds impossible to achieve this, but believe me, our place has made up, has gathered some experience on how to get these things to work. Okay, and with this, I'd like to close. So we've been talking about impact in software engineering research. Work on a real problem, real as in real world, not real papers, real world. Assume as little as possible can help if you make things fit into real processes. Keeping things simple helps in communication, helps in teaching, helps in having impact, helps in people remembering you. Having a sound model is necessary, such that you're not confronted with the interjection that everything you do is just ad hoc and a collection of recipes. No, come up with a sound model. Keep on learning. This is for your personal development. Go outside of your comfort zone and learn things about classifiers, about statistics, about user studies, about symbolic execution, about microarchitecture, about security, whatever. Dip your toes into things such that you get a broad view on things, and try this out yourself again and again, just in order to find out where the pain points are. And for this, you need to keep moving to new fields when your current fields are too crowded, such that you find new places where you can make a difference. And always try out things with prototypes, learn where the pain points are, and also build such prototypes for your own research, such that you get your algorithms right before you go and embark into re-implementing them in some much, much larger scale. With this, I'm already at the end of my talk, and I am happy to take questions. I think we have some time left for that. Thank you very much.